Well, let's just start here. So my first problem is a single box, but on an inclined plane. I'm not going to do a box on a flat surface because that's kind of trivial. But this is a box on a plane which is inclined. So a 10 kilogram box is on a plane which is inclined at 45 degrees, and there's a coefficient of kinetic friction. Kinetic means that it's actually going to be moving. Okay, so there's a coefficient of kinetic friction, 0.35. And I asked two questions: what's the net force, and what's the acceleration? Okay, so just like your kinematics problems, with these dynamics problems, you start off by drawing a diagram. And the first diagram you want to draw is just exactly what you would see if you walked into a lab. And in fact, you're going to be doing a lab like this. You're going to have an inclined plane, and you're going to put a block on it and let the block slide downhill, and you'll actually get static friction and kinetic and static friction out of it. Okay, so let me switch to my other whiteboard here, like that, and let me start drawing. So we have a plane, so it's inclined at 45 degrees like this. All right, so that angle in there is 45 degrees, and there's a box on it like this. All right. And there we go. Okay, and that's what you would physically see. All right, you see here in the chat, 3 people are in the chat. All right, well, let me continue. Um, uh, there's a box like that, and once you've got the actual physical drawing, the next thing is that you want to draw the forces that are acting on this box. And let's keep in mind why we want to do that. It's to get the F net. Okay, so all of this is to get F net, because that comes into Newton's second law, which says that F net is equal to ma. Okay, and to get F net, it's actually a vector, and so we have to do a vector sum of all the forces on this box. And to do that vector sum, you have to resolve them into their components. And so it's best to start off by drawing these vectors and decomposing them into x and y components right off the right at the very beginning. So I like to start with gravity, okay? And to draw the gravitational force on this box, I'm going to put a dot in the middle. Now, gravity technically acts everywhere on the box, okay? So we'll talk about that later. We'll have a more sophisticated idea of where gravity acts when we do rotational motion, which is the last topic in the course. But for now, we can, in these problems, approximate gravity as just acting right at the very center of the box, okay? And technically speaking, gravity acts straight down like that, okay? So that's how you would draw your gravitational force. But because we're going to be doing this vector sum that I mentioned, it's probably best to start by not drawing this vector, but drawing its components, and drawing the components which are perpendicular to the box, and drawing the components which are parallel to the box, okay? So I'm going to remove this vector right away, and I'm going to replace it with its two component vectors. One vector is the one perpendicular to the box, and another one is parallel to the box. If you add those two vectors together, they should give you exactly this vector which I drew just a minute ago, okay? But we're going to break them up into two pieces, because what we want to do is we want to get, this kind of characteristic cross, where you have only perpendicular components adding to other perpendicular components, and parallel components adding to parallel components, okay? And to calculate the perpendicular component, that turns out to be mg cosine theta, like that, okay? Now, I showed you why it's the cosine in the pre-recorded lecture. I'm not going to go over that again, okay? But it turns out that, there's some geometry here. And this one, the perpendicular component, turns out to be mg cosine theta, all right? And the other one is mg sine theta, all right? Now, rather than going through that geometry over and over and over again in your head, like rethinking it each time, it's probably best just to memorize that the perpendicular component is cosine, and then of course the other one has to be the sine. Okay, so the parallel component is the sine. All right, so I'll work out those values on the other whiteboard. It's kind of hard to write here, but there we go. That's gravity, and that's the first force that I usually like to look at when I do these problems. Okay, and the next force is the normal force. And the normal force, whenever you have two surfaces that are touching, like here you can see here the red that I'm drawing in there, that's the interface, the touching between the box and the surface of the plane. Okay, whenever there are two surfaces touching, there's a touching force, and that force acts perpendicular to the surface, so it's called a normal force. And so that normal force, it's perpendicular to those two touching surfaces. There it is. and we will call that Fn, like that. And then you ask, are there any other forces? And yes, there is. There's frictional force. And the way friction works is it always acts opposite the direction of the velocity. So if the velocity is downhill, like this box is slipping downhill, well, then there's going to be a frictional force. I'll do it in green, which is uphill like that. Okay. And this is actually kinetic friction, which we've been calling FF, like that. Okay. So there we go. There's the force of kinetic friction, uphill like that. And you ask, are there any other forces? Well, not really. The only other force, and it's not in this problem, but another force is like a tension if there were a string, but there's no string attaching this to anything else. And so that's it. Those are all the forces that are they're acting on this. Okay, and you can see the two blue forces are the gravitational force, and I've broken them up into their components. And now you can see why. We get this kind of characteristic cross here, where you have the uh, forces which are acting perpendicular to the plane, and they combine with one another, and then there are the forces that are acting parallel to the plane, and they combine with one another. Okay, so like this force here, the normal force, it will compete with the gravitational force, irrespective of the other two, because they're perpendicular. So whatever the frictional force is, or whatever the parallel gravitational force is, that doesn't matter. Those two forces are going to compete with one another, and so when we go to calculate F net, we compare those two. Okay, and similarly, this force downhill like that, parallel downhill, and this frictional force uphill, they also compete with one another to give you a total force downhill. All right, and so that's why we broke them up. We broke up gravity this way. If we hadn't, then like it would have been part of gravity competing with the normal force and part of gravity competing with the frictional force. So you really have to break it up into its two component pieces. All right. So let's see here, 3 people watching, and I don't see any questions. So let me switch right now to my other screen so that I can do some calculations. And so we've got 4 components here. We've got the gravity parallel, gravity perpendicular, the normal force, and the frictional force. And let's work them out. Okay. So over here, actually, let me cut and paste this because this way I don't waste your time with just a lot of typing. All right. So there's 2 parts to the gravitational force. There's the gravitational, can you see that? Not quite. Let me scroll down a bit. Okay, so there's the gravitational force parallel, okay, and that was, you saw a minute ago, was mg sine theta, all right, and in this problem, m is 10 kilograms. G, so there's 10. G is technically 9.8, but you know that we're rounding off to 10 to make our life easier. And then it's sine of theta, and theta, the angle, is 45 degrees. So sine of 45 degrees. And if you work that out through your calculator, that's going to give you 70.7 newtons, and it's downhill. Okay, downhill. Now, if you do the perpendicular component of the gravitational force, the equation there is mg cosine theta. Okay, and m is 10. G is 10 as well, and cosine of 45 degrees. It turns out that cosine of 45 degrees is exactly equal to sine of 45 degrees, like 0.707 and then some extra decibels after that. But cosine of 45 degrees, 0.707 multiplied by 100, and you get 70.7. So it just turns out, because it's 45 degrees, that the parallel and the perpendicular component are equal here. They're not in general, but you should know some of these special angles, like the sine of 30 degrees is a half, the cosine of 60 degrees is a half, and the sine and the cosine of 45 degrees are equal to one another, and they're like 0.707. Okay, so that tells us that takes care of the gravitational force. Next, let's look at the normal force. There's 2 more forces. There's the normal force, which I'll call Fn, and the frictional force, Ff. And you say, what are these equal to? All right. And let's go back to the diagram like this. Oops. Let's go back to the diagram here like that. And let's take a look. All right. So unlike kinematics, where it's mostly plugging into equations, here a lot of this is conceptual, which is what makes these problems a bit difficult. All right, so we now know that this is 70. Oh, let me do it in blue here like that. We know that this is 70.7 newtons. Okay, and we know this one is 70.7. Okay. And that, of course, we found with these equations. But to find Fn, there isn't really an equation. I mean, I guess you could say it's Newton's second law. But what you have to realize is that, as I said a minute ago, that is competing with the 70.7 newtons. Okay? So if it's competing like that, you ask yourself, well, which one's winning? Well, if the normal force is winning, then what would happen is that what that would mean is that the perpendicular component of the force is greater away from the plane, above, pulling up off of the plane, than into the plane. And what would happen is the entire box would actually lift off the plane. Okay, so you can't have that Fn is bigger than that 70.7, otherwise the box would actually lift off of the plane. Okay, well, what if Fn is smaller? In other words, the 70.7 is bigger. Well, then this box would be accelerating into the plane. It'd be like digging into it as it goes downhill, and that's not happening. The box is neither lifting off of the plane nor is it digging into the plane. And so these two forces must exactly cancel against one another. They're like playing a game of tug of war, and they're pulling against one another. They have to exactly cancel, otherwise whichever one wins, that's the direction in which it would accelerate, and it's not accelerating off of the plane or into the plane. And so you can conclude that the normal force must be also 70.7, and there you go. Okay, so not really an equation there. All it was just reasoning, and you're really reasoning using, I guess, Newton's first law, which says that if there's no there's no acceleration, there's no net force. Now, it's technically speaking no net force in the perpendicular direction, like this, up and down out of the plane. Okay, so it's not parallel. Okay, because those two are actually independent of one another, which is why we resolved everything into this characteristic x. Okay, so back over here in our other screen here, I can say Fn is equal to 70.7 newtons. And again, you say, well, how did you get that? It's just through the reasoning that I used, all right? And then finally, there's the force of friction. And you say, well, how do you get the force of friction? So kinetic friction is different than static friction, which is why in part A here I did a kinetic friction, and I'm going to do a static right after it, because I want to show you how kinetic and static are really quite different than one another. Okay, even though they're both called friction, they actually, to solve them, you approach them in very different ways. Okay, so for kinetic friction, there's a formula, and I don't have my little mu symbol, but basically the way you get the force of kinetic friction is you take the coefficient of kinetic friction and you multiply it by Fn, like that. Okay, and the coefficient of kinetic friction, I give it to you, it's 0.35, like that. And the normal force is 0.707, like that. And that turns out to be equal to, let me get that answer for you, 24.7 newtons, and it's actually uphill, okay, which you can see from the diagram. All right, so it turns out to be 27.4. Now, how do you understand this formula? Like, if you want an intuition into this formula, how do you understand it? So friction, it depends on two surfaces touching, and whenever there are two surfaces touching, there's a normal force. And what happens is that the harder the two surfaces are pushing up against one another, in other words, the bigger the normal force, the more they're sticking together, and the more they're sticking together, the more friction there is. Okay, so in other words, the harder they press against one another, the more friction there is, and the coefficient of friction is kind of like the percentage. Okay, so like 0.35, that just says that the frictional force is 35% of the normal force. That's the way to think about this. Okay, and so now we have all four components. Let's switch back to our diagram so we can see them all together. Okay, and so over here, let me do this in green. Now I know that this is equal to 24.7 newtons, like that. Okay, and you work this way, where like you do a little bit of calculation and go back to the diagram and write in the numbers, and then once you have all the components, you can now work out what this F net is. Okay, and again, there are two components to F net because it's a vector. All right, so the perpendicular component, that's easy because we already reasoned that one out. The two have to cancel one another, and so there's no perpendicular component to F net. The perpendicular component to F net is 0 because the box isn't accelerating into the plane or perpendicular to the plane in any way. Okay, it's the other one, it's the parallel, which gives rise to an F net, okay? And so what you have here is a tug of war between the component, the parallel component of gravity downhill, and the force of friction uphill, okay? And the parallel component downhill is 70.7, so it's pulling down 70.7 newtons, but friction is pulling up 24.7, and you say, well, which one wins? Well, obviously, the force of gravity wins, okay, so that's the bigger force, and you say, but, it has to overcome the frictional force, so the total force downhill is going to be 70.7 minus 24, which is, I guess, 46. Okay, so let me switch back to the other screen here like that. Okay, and now we can write in on the next line, F net is equal to, just from the analysis we did, downhill, there's parallel gravity downhill, and that's 70.7, minus the frictional force uphill, and that was 24.7 like that, and that works out to be 46 newtons like that. And of course, one's downhill, one's uphill, but the downhill wins, and so the overall is downhill like that. Okay, so there you go. Did we answer the question? What is the net force? Yeah, we did. The net force is 46 newtons downhill. Okay. All right. So let me see if there's any questions in the chat there. Is everyone okay? I don't know. I didn't get any responses earlier about whether you can hear my audio, but I'm assuming that at this point you would have told me if you couldn't hear the audio. Okay. So let's go on to the next question, which is what's the acceleration? Well, like Newton's second law is basically, F net is equal to ma, like that, okay? And so all of this work, the whole point of all of this work, and in a lot of these problems, there's a lot of work, in terms of the analyzing the forces, all of that work is to get F net, okay? Because F net is what comes into the second law. Okay, so that says that. Now, we don't want to solve for F net, we want to solve for A, and so let me just rearrange this equation, divide both sides by m, and so we get that F net, A is equal to F net divided by m like that. And so that's going to be what? F net we found to be 46 newtons, and m we said was 10 kilograms like that, and so that turns out to be 4.6 meters per second squared like that. Okay, and the direction, Newton's second law, not only tells you how to calculate the acceleration, but also tells you that the direction of F net and the direction of the acceleration have to be the same, and so obviously the acceleration is in the same direction as F net. Okay, so that solves that answers that second question. What is the acceleration? You should always ask yourself the question, does 4.6 meters per second squared make sense? Well, it has to be bigger than 0, otherwise it's it's not moving. It could be moving downhill at a constant velocity, but it wouldn't be, if we start off at 0 velocity, it wouldn't be moving downhill if it had no acceleration, because it wouldn't start moving downhill. And it can't be bigger than 10, because that means that's free fall, and it's not free falling, it's falling along along this wedge here. And so, yeah, that makes sense. Okay, it's like 4.6. That makes sense. All right. So that answers our first problem. Okay, let me take a look here in the chat. All right. Well, 3 people still listening. I didn't get any answer to my "Is everyone okay?" So I assume you're following along here. Okay. And that's the first one. Now that one will get you through the first few questions. I don't remember how many, but my first question in the assignment, to be honest, I don't quite remember it because I made it up over a week ago. But I remember doing a problem of a box on a wedge, okay, like this, or on an inclined plane. And so this is the first part of it. The next one we're going to do, let's move on to the second problem here. Oh, I'm sorry. We're not quite done with this one. So that was the situation with kinetic. Okay. So now we're going to do static. So I say repeat the entire problem. Okay. But this time the box doesn't accelerate. All right. And I asked to find the force of static friction. So to do that, let's go back to the diagram, because that's your first step. Draw the diagram again. Okay. So let me start over. create a new whiteboard here like that. Did it work? Yep. Okay, and here's my wedge like this. Whoops, that's a bit too steep. All right, there's my wedge at 45 degrees. All right. And here's a box like this. All right. And we've got forces on it. We got the force of gravity, but right away I'm going to draw that force of gravity as mg cosine theta, like this, and mg sine theta. Okay. And you ask yourself, is that all the forces? Nope. There's a normal force, because as soon as you have surfaces touching, you've got a normal force. So there we go. There's my normal force. And is that it? Nope. There's a static friction force like this, and this time we'll call it Fs because it's static friction. And now you ask yourself, is that all the forces? And yeah, that's it. Those are all the forces. Okay. Now, at this point, because it's the same problem as before, well, almost the same problem. This time the acceleration is 0. Okay. All the numbers when we go to calculate things like mg cosine theta and mg sine theta, they're the same. Okay. So this number here, whoops, let me do that in blue. This one is going to turn out to be 70.7 newtons. Okay. And this one's going to turn out to be 70.7 newtons. All right. And now let's see if we can work out what these other two forces are. Okay. So we take a look at the normal force, and of course it's competing against this force, and you ask yourself, is this box accelerating up, like in the normal force direction? Is it accelerating into the plane? And the answer is no, just like above. And so these two forces, they have to cancel against one another. And so you can immediately conclude that this is 70.7 newtons. Okay. So far, the reasoning is identical to the previous problem. But in some sense, here we're starting from a different point. We're starting from the realization that since the acceleration is 0, the total net force is 0. So we're not trying to find the net force. In a sense, we're actually doing this in the opposite direction. We're starting from the point, from the conclusion that the net force must be 0, and then all of these forces must turn out to be 0. Okay, so you don't calculate Fs using some formula. You simply, just like we determined that Fn had to be 70.7 newtons, using the same logic, you say, well, Fs must equal this force here, because the two have to cancel. Because if they didn't, then F net would not be 0, and if F net is not 0, then there would be an acceleration. Okay, so it's the same kind of reasoning that we used for the normal force, we use for Fs, and we realized that it must also equal 70.7 newtons, because if it didn't, then you'd have an acceleration. Okay, so let's go through that logic again. If this force here were bigger, that's the parallel force downhill, if that were bigger than the frictional force, then who would win? Well, then the gravitational force would win, and it would accelerate downhill. Okay. Conversely, if the static friction uphill were bigger than the force of gravity downhill, the static friction would win, and it would accelerate uphill, which it doesn't do. It doesn't do either of those things. So these two can't be different than one another. They must be equal so that they cancel to give you a 0 net force. Okay, and that's why this has to be 70.7. So it turns out in this problem, because the angle is 45 degrees, it turns out in this problem that all the components are 70.7 newtons. Okay, now once you have that, we can go back to our other whiteboard here, and we can write down what we found. And let me just cut and paste that, because why not? Here's the reasoning. Okay, and the conclusion. Since A had to be 0, right? Because there's no acceleration. So since A has to be 0, F net has to be 0. So for F net in order for F net to be 0, these two, they're the same. Well, then in order for this to be 0, we concluded that the normal force was 70.7 and the force of static friction was also 70.7. Okay? And so we can answer the first question. Okay, the first question is, what is the force of static friction? And it turns out that the force of static friction is 70.7 newtons, like that. Okay? Now, the next question was, show that the coefficient of static friction is in fact greater than tangent of theta. Okay, now why? In the pre-recorded lectures, I actually proved that for an inclined plane, that if there's static friction, okay, the coefficient of static friction has to be bigger than the tangent of theta. And in fact, you're going to prove that in your lab, or you're going to demonstrate that experimentally in one of your labs, okay? And so let's see that that actually turns out to be true, okay? So the coefficient of static friction, all right, it's has to be bigger than or equal to the force of static friction, whoops, the force of static friction divided by the normal force, like that, okay? Notice that this is not an equality, it's an inequality. So that means that I can't tell you what the coefficient of static friction is going to be. I can only tell you what it can't be smaller than. It has to be bigger than this ratio here, but it can't be smaller than that ratio. If it's smaller than that ratio, then the box is going to slip and you don't have static friction. If it's bigger, then you're okay. Now, how much bigger, I can't say, okay, but it's got to be bigger. Now, what is that value? Well, it's pretty easy because static friction was 70.7 newtons and the normal force was 70.7 newtons, like that, and that's equal to 1. Okay, and so the coefficient of static friction has to be bigger than 1, like that. All right, and so it could be 2, it could be 10, it could be 100, okay, it could be 1.1. As long as it's bigger than 1, the box will not slip downhill, okay? It can't be 0.9, then it would slip. It can't be 0.7 or anything like that, all right? Now, this number 1 here, actually, like I said, I proved that it's actually equal to 1. And so if you do the tangent of 45 degrees like that, and you plug that into your calculator, sure enough, it turns out to be 1. Okay, so you know, this is not new. You can certainly make use of tangent of theta for the coefficient of static friction on an inclined plane, okay, with a single box. You can make use of that formula, but you know, this example does illustrate that. Okay, so that completes our first example. Let's see if there's any questions in the chat. Okay, any questions? I'll type it in as well. All right. If not, there's our first problem. Okay. And again, it's very similar to the one that you have on in the assignment. Let's do our second question here. Okay. So now we're ready for the second question. So this one is different because this is an example where we have two boxes, and the two boxes are actually connected by a string. Okay, and so we're going to find the acceleration of the entire system. So what does it say? A 13 kilogram box on a flat table with a coefficient of kinetic friction 0.25 is attached by a string to a 6 kilogram box dangling off of the end. Okay, what is the acceleration of the system? All right, so like always, we're going to start off by drawing a diagram. Switch to this. Let's create a new fresh board here, like that. Okay, and step number 1 in drawing the diagram is just draw what you would physically see. Okay, there's our table. There's my 13 kilogram box, like this. Here's my 6 kilogram box dangling off of the end, like that. Okay, and there's a string. Here's the string, and then there's a string this way, like that. And the string goes around a pulley. I didn't mention that in the problem, but it's implicit. Whoops, let me make that a little bit nicer. There's my pulley, okay, like this, and there you go. Okay, that's what you would physically see. And this one up here, this is the 13 kilogram because that's the one sitting on the table, and this is the 6 kilogram off the end. All right, okay, so there's step number 1. Now step number 2 was to identify all the forces. But you identify all the forces for each of the masses that are involved. And in this case, there are two masses. There's this one, and independently, there's that one right there. Okay, so there are two masses. And so we got to do the forces for each one of them. All right, let's start off with gravity because it's always good to start with gravity. Gravitational force for this one is going to equal mg, but there are two m's, so don't confuse them. Let's call this one m1g. Okay, and that's going to equal 13 multiplied by 10. I'll try to do the math right here, but it'll be a little sloppy, but I think I can do it. There you go. That'll be 130 newtons. Now we should probably finish this one off first, but it's okay. We can add gravity for this one. Let's do that just to show you that they're different. I mean, it's still the same formula, but because it's a different mass, we'll call this one m2g. This time for this one, you're not going to put in 13. You're going to put in 6. Okay, so 6 times 10, and that gives us a total of 60 newtons, like that. Okay, 60 newtons. All right. So, all right, let's go back to the first one. Okay, so we got gravity in the first one. Are there any other forces acting on the first one? Yeah. Okay, there is normal. Let's do that one next. Okay, so here's our normal force, Fn. And then you say, well, is there any other force? Is there friction? Yeah, there's friction. And now, which way is this thing going to move? Well, let me do the acceleration in red here. This thing is going to accelerate that way as this box accelerates down that way. Okay, so the 13 kilogram is going to move to the right, and the 6 kilogram is going to move down. Okay, and it's going to accelerate. So if it's accelerating to the right, it's going to have a velocity to the right, and so there's going to be a frictional force, and it's kinetic friction to the left, like that. Okay, so there we go. There's our force of kinetic friction, like that. All right. And you ask, is there any other force on this thing? Last time, those were the only forces we had, was gravity, normal, and friction. But there's another one. I'll do this one in purple because there's a string, and it's a string that's pulling this thing forward. And so there's a force like that, and we will call that the tension. Okay, Ft, like that. All right. So there turns out to be 4 forces there, like that. Okay, now we've identified all of them. We'll try to put some numbers on them in a minute. We did already for gravity because the reason I did the gravity is because I wanted to show you how they were different. Okay, this is a mistake that I've seen made where students will sometimes confuse the 6 kilogram and the 13, and they'll say, oh, I've got a mass, and they'll just like plug it in for any old m, and then you get the wrong value. Of course, it makes sense that the gravitational force on the 13 kilogram is 130, whereas the gravitational force on the 6 kilogram is only 60 newtons. Okay, so let's see if we can identify any of the other numbers here. Let's see if we can do the normal force. So ask yourself, is this thing accelerating either up or down? And the answer is no. So that means that the normal force up must balance the gravity down, and that's 130 newtons. Okay, the reasoning is identical to before. This has to cancel that one. Otherwise, the box would either be accelerating up or accelerating down, and it can't do either of those things, or it's not doing either of those things. Okay, and now the next thing is, do we have the frictional force? And the answer is yes. And let me see if I can calculate it over here. Okay, so once you've got the normal force, the frictional force is a fraction of the normal force, and that fraction is given by mu k. Okay, and that's how you do that's how you draw the coefficient of kinetic friction. So it's mu k times Fn, like that. And mu k, what did I say it was? It was 25%. Okay, so it's 0.25, like this, multiplied by the normal force, which is 130 newtons, like that. And that's going to equal, what does it equal? Let me look up my answer here. It equals 32.5. So over here, this is equal to 32.5 newtons. Okay. Great, we've got 3 of them. Do we know how big the tension is? And the answer is no, we don't. Okay. Don't do something like, I don't know, like, oh, the tension has to balance against that one and those two are equal to one another. No, it isn't. Otherwise, you wouldn't have any acceleration. We simply don't know how big the tension is. And so we can't assign a number to the net force right now for box number 1. Okay, for a 13 kilogram box. Okay. All right, so we're kind of done, or we've gone as far as we can with our analysis of the 13 kilogram box. Let's turn our attention to the 6 kilogram. What forces are acting on it? Well, we already identified gravity down. Is there another one? Yeah, there's the string pulling up, and that's got a force Ft, and that's also question mark. Okay. Now there's a couple of things here. This tension and this tension are exactly equal to one another, okay? Which is why I didn't put any subscripts. I didn't say Ft1 and Ft2. Those two tensions are exactly the same. And the reason is it's the third law. It's Newton's third law, okay? Acting along the string, all right? And you say, well, why is it the third law? Well, what does the third law say? It says if there's a force of one object on the other, then the other object pulls back on the first one with equal force, but in the opposite direction, okay? So equal force, opposite direction. So if you take a look at these, you go, okay, well, you told me that they're equal, but they're not in the opposite direction because, you know, one's to the left and the other one's up, or so one's to the right and the other one's up. And you go, well, what's going on here? Like, is that really the third law? Yeah, it is. The thing is we're being a little bit sloppy. To do the third law properly, you have to take into consideration the pulley there. And if you do the pulley, you'll see that the only effect that the pulley has is to not change the magnitude of the tension. It just changes the direction. And that's why you get the same magnitude, but not opposite direction because the pulley is changing the direction, okay? Now, I didn't do a full analysis of that in my pre-recorded lectures. I'm not going to do that now. It can be done. It's not that hard, but it really doesn't add any intuition to the problem. So yeah, these two tensions, they are equal to one another because of the third law, and the direction is modified because of the existence of the pulley. Okay, but they are the same. Okay. By the way, you might ask the question, are the accelerations the same? Okay, because I automatically assume that both blocks were going to accelerate the same, and the answer is yes. Because as long as the string doesn't stretch and doesn't like bunch up, okay, we're going to assume that it doesn't stretch, then, you know, the 6 kilogram, if it moves down 1 centimeter, then, you know, then the 13 kilogram has to move the same. If the 6 kilogram moves further than the 13 kilogram, well, then the string must be stretching, okay? And so since the string remains taut throughout the whole process, these two accelerations have to be the same. And that's why I didn't call one acceleration 1 and the other one acceleration 2. They're both the same accelerations, okay? But the masses were different, so I called this one M1 and I called that one M2, okay? So that just to give you the logic of how I worked that one out. Okay, so now that we've done this analysis, we've got the forces, not completely, we don't have Ft, but we've gone as far as we can. Let's switch back to our other screen here, like that. And let me show you what we have for the 13 kilogram box here. Where's mine? Okay, here it is. We called it M1 like that. We have the following. We have that its weight, its mass, M1G like that, was equal to 130 newtons. Hold on here, can you see that? Yep, okay, that's good. Okay, 130 newtons, so there's the weight. Then there was the normal force, and the normal force turned out to be 130 newtons, like that, because the two had to cancel against one another. There was also the frictional force, which we worked out to be 0.25 times 130, okay? And there was the tension, which is just unknown. We simply do not know how big the tension is, okay? And so at this point, you could say, well, what's F net? And you might say, well, I can't calculate F net because I don't know one of them, but you kind of can. You can at least, you know, push F net as far as you can determine it. So let's go back to the diagram for a second to see how we would reason out F net. Okay, and so these two forces here, the normal and gravity straight down, they cancel. Okay, so they're not contributing to F net at all. You can just strike them out like that. Okay, it's these two that are competing. All right, and which one has to win? Well, the one that has to win is Ft, because if Ft if F were bigger, then it would be accelerating that way, right? If the force of friction were bigger to the left than the tension to the right, the force of friction would win and it would accelerate to the left. But it isn't. It's accelerating to the right here like that. And so the tension has to beat the force of friction. And so over here we could write, okay, which one's winning? The force of tension is winning. Tension is winning over the force of friction, like that. And we don't have a number for the tension, but we do have a number for friction, 32.5, and that's it. That's as far as you can really go with that. Okay, you really can't say anything else. All right. At this point, you go, well, now what do I do? Having done this with students a few times, this is the point at which students usually get confused. Never forget that once you get F net, even if it's an incomplete expression like that, the whole reason you got F net was to say that F net is equal to ma, which is Newton's second law. Okay, so that's why we got F net. That's why we did all of this work to get F net, and we got F net so we could set F net equal to ma. Now, which m? It's actually m1 like that. Okay. And so at this point, you could say, all right, fine, F net, we don't have a number for it, but we do have an expression. There it is. So do it like that. Okay. So I can't put a number enough for F net, but at least I can go part of the way there and put Ft minus 32.5. That's got to equal. Do I have a number for M1? Yep, 13. Do I have a number for 8? Nope. And so that's it. That's as far as you can go, and we'll call that equation number 1. You can't solve it yet, but it's something. All right. And great. So now what? So now we'll turn our attention to M2, and M2 is the 6 kilogram. Okay, there were two forces acting on it. There was M2G like this. All right. So M2G is equal to 60 newtons. All right. And then there was also Ft acting on it. Put a space in there. But guess what? We don't know how big Ft is. All right. We didn't know over here, and it's the same Ft. We don't know it over there. Didn't know Ft here. We don't know Ft there. Okay. And why did we do all this? Those are the only two forces. Why did we identify all the forces? So that we can get F net. And you say, all right, now what? What do you put in there? Let's go back to the diagram. All right. So if you take a look here in the diagram, we're looking at this situation over here with the 6 kilogram mass. It's accelerating down. Okay, it's being pulled down by gravity. And there are two forces. There's 60 newtons pulling down, and there's Ft pulling up. Which one wins? Well, the 60 newtons down wins. Okay, has to win, because if it didn't, then if the Ft wins, then it would accelerate up. So the 60 newtons down beats the Ft up. Okay, and so we can say that the net force must be the 60 newtons minus whatever the tension is, like that. Okay, so we don't have a number for F net, but that's okay. We didn't have a number up here either. The best we could do was, the best we could do for F net is get an expression. All right, so now why did we do this? We did this so that we could use Newton's second law. So this here, this line right here, you say, where did that come from? That's the second law. Okay, well, where did this line come from? Oops, hold on. Where did this line come from? Only with M2. It's also the second law. Okay, now the second law, but now applied to the 6 kilogram. And so this one's equal to 60 minus Ft, and that's going to equal M2. And what's M2 equal to? 6 times A. And there we go. That's as far as we can go. Okay, if we had Ft, we could solve for A, but we can't. Okay, and you say, well, now what do I do? Well, what you do is, the rest is really just math. What you do is you put these two equations together. You put this one here, all right, and you put this one underneath like this. Okay, and what you do is, it's very easy to solve. It's two equations and two unknowns. All you have to do is add the left-hand side to the left-hand side and the right-hand side to the right-hand side, and you get, the Ft cancels out. So there's one plus, there's the other one, like that. Okay, and that's going to equal this one plus that one, like that. Okay. And you'll notice that ft here cancels ft there. So you're just going to have, well, I'll put it in another line. You're going to have that is equal to, and 13 plus 6, what's that equal to? 19. All right. And then 60 minus 32 is, here I've got the, is 27.5, like this. And that's going to equal 19a. And so a is going to equal, let me get the answer. It's going to equal 1.45 meters per second squared. All right. So that solves that one. Okay. So great. Did we answer the question? I asked what is the acceleration of the system, and we got that the acceleration was 1.45 meters per second squared. Okay, and does that make sense? Yeah, it has to be bigger than 0 if it's accelerating at all, and it has to be less than 9.8 or 10 meters per second squared. Okay, and 1.4 is less than 10. So yeah, it works. Now I'm going to ask you to do this one on your own. Okay, and I'll do it on Friday, but think about this one on your own, and because it brings up static friction. So I say repeat, but this time the system doesn't move at all. So in other words, this time the acceleration is 0. Okay, and just like before, like in this problem, see what we did is we had to do all this analysis and then we ended up with the acceleration. This time it's like you start with the acceleration and then you end up with the particular forces. Okay, so if the acceleration is 0, what happens? Well, let's go back to the diagram very quickly and I'll show you, or I'll give you a hint how this works out. Okay, so ft now is not unknown. Ft, since this is 60, ft has to cancel that 60, so ft here is 60. All right, because 60 up and 60 down, they cancel, and that's what leads to no acceleration for the 6 kilogram mass here. Now if this is 60, then this one must be 60. Okay, so that those two, because those two are equal to one another. And if this is 60, then guess what? The force of friction has to also be 60. Remember, this is kinetic friction, so now we're going to replace that with static friction. If this is 60, ft is 60, then F static friction has to be 60, and you get that the force of friction is 60. And then you have all of the forces for this one. You're going to have 130 up, 130 down, 60 to the right, 60 to the left, and you've basically got all the forces there. And then finally, to solve for the coefficient, you make use of this formula here, just like we did above. You make use of that. Okay, today I'm just going to continue with the problems that we were doing last time. We finished one problem, which was just a single mass, single box on a inclined plane. And today we're going to do two boxes that are attached by a string. We already did part A of question number 2, and that is with a flat table, and there was a box on a flat table and another one dangling off of the end. We didn't do part B, so we'll pick up from there, and then we'll also do another question number 3 here. And question number 3 will actually sort of combine question 1 and 2. I'll put a box on an inclined plane, but it's also attached to another box which is dangling over the end. Okay, so let's start reading question number 2 here. Part A, a 13 kilogram box on a flat table with a coefficient of kinetic friction 0.25 is attached by a string to a 6 kilogram box dangling off of the end. What is the acceleration of the system? Okay, so like I said, we finished that one, and this is the kinetic example. Today we're going to do the static equivalent of that one. Okay, so we're going to repeat the whole thing, but we're going to assume that maybe the table surface is different or something like that, and the box is actually going to stick to the tabletop. It's not going to be able to move, so there's enough friction to prevent it from sliding. And I want you to find the coefficient of static friction this time. Okay, now technically speaking, you're not going to find a value, you're going to find a range for the coefficient, and that's because as long as the coefficient is above some minimum, the box won't slide. It's only if it's below that it would slide and you wouldn't be in the static situation. Okay, so let's begin and begin by drawing a picture. So here's the tabletop, like that. It's a flat table, And here's the 13 kilogram box, which is on the flat tabletop. Okay. And we have a 6 kilogram mass here like that. And the two are attached to one another by a string. And there's a pulley keeping the string in place like that. Okay, so there's physically what you would see. And the next step is to start putting in the forces, doing the free body diagrams for each of the masses. Now there are two masses, obviously, and so we're going to have to do two independent free body diagrams. Okay, and so let's actually do the free body diagram for the 6 kilogram first. And the reason for that is that you'll see immediately how this is different than the kinetic friction problem. Okay, so the first force that we'll look at is gravity, straight down. Okay, and it's calculated by mg, but we'll call this one m2g because there are two different masses. Okay, so there's this one is m2 and this one is m1 here like that. Okay, so m2g, and if you multiply 6 times g, will round off to 10. That's 60 newtons like that. And there you go. That's the weight of the box. Okay. Now, if that's the only force that there would be on the box, it would just be free falling. So there is another force which is preventing it from moving, and that is the force of tension up due to the string. And we are in the static situation, which means that F net must equal 0 for both boxes. Okay? Like if you're not moving, then acceleration is 0, and if the acceleration is 0, then the net force has to be 0. And so unlike the previous problem, the kinetic energy that we did on Wednesday, where I wasn't able to say what the tension was, I can immediately say what the tension is this time because these two have to cancel. Okay, you see, last time I couldn't say what it was because the box was dropping. And so the only thing I could say was that Ft was less than 60 newtons. But I couldn't give you an exact number. It had to be less than 60 newtons because this thing was going to be accelerating down like that. Okay? But this time it's not accelerating. All right? And so Ft has to exactly cancel the 60 newtons so that it's neither moving up nor moving down. All right? And so we've got immediately the value of Ft here. That's 60 newtons. Okay, so these static friction problems are actually easier because this criterion right here, F net equals 0, that allows me to actually specify more forces than you would if you have the object moving, okay, or accelerating. Okay, so that's it for the 6 kilogram mass. There are only two forces on it, gravity down and the tension up, and they cancel the way I've got them there. Okay, so now let's move on to the 13 kilogram box. There's the force of gravity down, and this one is equal to m1g. Okay, and m1 is 13 kilograms, and g is 10 meters per second squared, so that gives us a weight of 130 newtons. Okay, so that's it for the force of gravity, and we don't have to break it up into a parallel and perpendicular component because this is not inclined at all. It's just purely a perpendicular component. It's purely straight down. Okay, so next we'll look at the normal force, and the normal force is perpendicular to the surfaces here. So that's like the surfaces that are touching. Perpendicular means it'll be straight up like this, and there's Fn. We'll add the value in a minute. Okay, and then there's the tension pulling this forward like that. Okay, Ft. And there is static friction in the opposite direction like this. Force of static friction. All right, let's see if we can add any numbers to the normal force, the tension, and static friction. So the normal force has to cancel gravity down. All right, and so that's going to be 130 newtons. Remember, the net force is 0 every which way, so that's up and down have to cancel. The forces up and down have to cancel. Okay, the tension here Well, the tension is the same throughout the string. That's basically Newton's third law. Okay, so the tension is the same throughout the string. So if we know that the tension is 60 newtons over here, then it's going to be 60 newtons at the 13 kilogram box too. Okay, like that. All right, and so that's the tension. Now, um, imagine that we didn't add a force of friction here, static friction. What would happen? Well, like this force would cancel that force, but then you'd be unbalanced. You'd have like 60 newtons to the right, okay? But the box isn't going anywhere, so we need 60 newtons to the left in order to balance the forces, and so you can immediately conclude that the force of static friction is 60 newtons, okay? And again, that's because this force has to balance against that force, okay? Now, a common mistake that's made is that you use this formula mu s times Fn to calculate the static friction. That does not work here. I know it works for the kinetic friction, but this is not kinetic friction. This is static friction, okay? So in fact, it's not really an equality here. It's actually an inequality. And the inequality looks like this, okay? That the force of static friction is bigger than this number, all right? And so, in fact, that's what we're going to use to get mu s. But you don't get a number; you get a range, okay? But you don't use this to determine the force of static friction. The way you determine the force of static friction is by just the way I showed you. You say, well, this has to be whatever is needed such that the box doesn't move. So if I remove that force, well, then it would be unbalanced and you'd have 60 newtons to the right, and so you have to have 60 newtons to the left in the form of friction to prevent it from going anywhere, okay? And so that determines that specifies our value for the force of static friction. All right, let me take a look in the chat here if there's any questions. Okay, everyone okay so far? All right, well, okay, this is kind of nice because, like, unlike the kinetic friction where we didn't know Ft, and so Ft was like a question mark in those problems, and then we had to solve two equations and two unknowns. Here we have all of the forces, okay? So let me switch back to my other board here, and we're going to solve this problem right here, or we're answering this problem right here. Find the coefficient of static friction. Well, the coefficient of static friction, okay, it's like I said, it's not, there isn't an equality for it, there's an inequality. The coefficient of static friction has to be bigger than or equal to the force of static friction divided by the normal force, like that, okay? And so we can substitute in now for those, and for static friction we had 60 newtons. For the normal force we had, let me look, 130 newtons, okay? 130 newtons, and so this is going to equal, let me quickly work that out for you, 60 divided by 130 is this number right here, rounding it off, okay? So there it is. There's the coefficient of static friction. So it's an inequality. Let me just rewrite it down here. I can't tell you exactly what the value is. All I can tell you is that whatever the value is, it has to be bigger than 0.462, okay? Like it could be 1 and then the box wouldn't move. It could be 2 and it wouldn't move. It could be 10, 1,000, whatever. As long as it's bigger than this number, it won't move. If it were less than this number, then you wouldn't have static friction, okay? What would happen is it would start to move. All right, so that's part B. And I know we did part A last time, but if you go back to part A, you'll see that there was a lot more steps to it than there were to part B. And again, that's because if we look at the diagram again, we were able to, by just using the fact that F net is equal to 0, we were able to identify all of the values of all the forces, okay? So the static friction problems generally are easier, all right? So let's move on to question number 3. And actually, I did this even for my other class. Rather than solving part A first, which is the kinetic friction part, okay? So it's moving. Let's actually do part B first, okay? So question number 3 is about as hard as I'm going to make your problems, okay? And you have one similar to it on the assignment, and there'll be something like it on the test as well. And so it's by far the most difficult type of problem. And so let's just take it in steps. It's easier to do the static friction problem. So let's do the static first, and then once we're done the static, so do part B first. Once we've done the static, we'll return to part A, and we'll do the kinetic friction. Okay, and actually, even though the numbers aren't the same, because one is kinetic, one's static, the static will give us some idea of what we're supposed to be doing for the kinetic friction. Okay. All right, so let's read the problem. Repeat 2A, in other words, repeat the same problem as before, but this time the 13 kilogram box is not on a flat table, but it's on a plane inclined at 30 degrees, okay? And the 6 kilogram box is trying to pull the 13 kilogram box uphill. It may not, okay, but that's what it's trying to do, okay? Also, the coefficient of kinetic friction is only 0.025 in this case, so it's a smoother surface, all right? And find the acceleration. So for my Physics 111 class, I actually started I wrote the problem and I didn't work it through, and I did the problem with 0.25, and towards the end I realized that it wasn't going to work out, and it's because I made my kinetic friction too big. Okay, so that's the danger of just making up numbers as you go along. Sometimes you'll come up with something unphysical, but it became pretty obvious, that it wasn't going to work out. So if you're wondering why did I change the kinetic friction from 0.25 to 0.025, that's why. Okay, it had to be smaller, otherwise the box wouldn't move. All right, and then part B is same setup, but this time nothing is going to move. Okay, so we're going to get the coefficient of static friction. It's exactly like part B from the previous problem. Okay, so let's start off by doing part B first. All right, so here we are, and let's get a new whiteboard going. Okay, and what does the diagram look like? Well, I said that the table was inclined at 30 degrees, so you have to watch that, because it could mean this, and the 13 kilogram box is here, and the 6 is there like that, and then there's a string like that pulling it like that. Okay, that would be inclined at 30 degrees if I made that 30 degrees in there. But if you read the other sentence, it says the 6 kilogram box, the 6 kilogram box is trying to pull the 13 kilogram box uphill, and that's not what's happening. The 6 here is trying to pull it downhill, and so this is not the situation we want. Okay, the situation is this. We have this situation here. Okay, and this angle in here is 30 degrees like that. All right, and you've got the 13 kilogram box here like this, and here's the 6 kilogram box off the end here like that, and here's a string which comes around like that and goes like that around a pulley here that's holding it in place. Okay, oh, let me try that again. Okay, good enough. Okay, and now you can see that the 6 kilogram is trying to pull the 13 kilogram uphill. Okay, and this is the 6 kilogram over here, and this is the 13 kilogram over there. Okay, so that's our first step. Draw the diagram exactly as you would see it in the lab, and there we go. Now what? Well, let's start with the 6 kilogram box just like we did last time, and let's see if we can identify all the forces. So there's a force of gravity, and that's straight down like this, and it's m2g, and it's still going to be 60 newtons. Okay, so there you go. There's your force of gravity, 60 newtons. None of the numbers change, so you're going to get the same value for the weight, 60 newtons. And then you have tension up like this. Okay, Ft. And we are in the static situation. So once again, we have that F net is equal to 0. What does that mean? It means that this force must cancel that force. They must cancel. And so this one's 60 newtons. Okay, that was easy enough. Okay. And there are no other forces on the 6 kilogram box. Okay, so we're done with the free body diagram there. Let's go to the 13 kilogram, and let's start off with gravity. We have gravity, 2 components, okay, like that and like that. All right, this component here is calculated by doing m, and we should call it m1g cosine theta, like that. And so m1 is 13, g is 10. The theta is 30 degrees, and that works out to, let me see here, I've got my answer written down from earlier. That turns out to be 112.6. 112.6 newtons. Okay, And the other one is, I mean, once you identify that one of them is the cosine, the other one has to be the sine. So if you just do m1g sine theta, you're going to get the value for this one, and this one turns out to be 65, okay? Newtons, all right? So m is 13, g is 10, so mg is 130. And sine of theta, sine of 30 degrees, sine of 30 degrees is one of these numbers that you should memorize. Sine of 30 degrees is a half. A half of 130 is 65. Okay, so mg sine theta will turn out to be 65. All right, so there we go. There's gravity already broken up into the parallel and perpendicular components. And let's now do the normal force. So let me show you a mistake that students often make. Well, not that often, but they make it sometimes. They think of the normal force as like the up force because, like you remember in the previous diagram, the normal force was up, and they'll do this. They'll draw the normal force like that. That's wrong. The normal force is normal. Normal is synonymous with perpendicular to the surface here. Okay? And so perpendicular to that is like that on an angle. I mean, you probably knew that, but I just wanted to, like, be very clear about it. All right? So F normal, and that's going to equal something. Let's determine the value in a minute and make sure we get all the forces first. And then there's tension, like this. That's Ft. And Ft here has to be the same value as there, 60 newtons, because the tension is the same throughout. 60 newtons, like that. And you know what, let's put in Fn. We know that it's going to be 112.6 newtons, like that. And there's got to be friction, but before we do that, let's take a look at what cancels right now. Okay, let me see if I can do it in maybe this orange will work. Oh, that's off. Let's try that one. Okay, so yeah, that's dark enough. That one will cancel that one, right? Okay, so the normal force will cancel the perpendicular component of gravity. Okay, and this force here, the parallel component of gravity, tries to cancel that one there, the 60 up, but notice that it's unbalanced. So it's 65 versus 60, which means that there's an extra 5 newtons down this way. Well, if there's an extra 5 newtons, what does that mean? If there's an extra 5 newtons down, it means it's going to start accelerating in the downwards direction. But it isn't. So we have to have that the net force is 0. And you say, well, how do you do that? Well, there's friction. And which way does that friction have to be? Well, it can't be down because then it's adding to the 65. And we want to subtract from the 65. And so over here, there's a force of friction. Let me draw it right here, like that. Fs. And you ask yourself, how big does Fs have to be such that this thing doesn't move? And well, we got 65 down, we got 60 up, we need another 5 up to balance it, and so that has to be 5 newtons. Okay. Once again, I didn't use a formula to reason out what the static friction is. I just simply said to myself, well, the force of static friction has to be whatever it has to be such that this box isn't going to move. Okay, and it became obvious that I had 65 down, so I need 65 up. I only had 60, so the other 5 had to come from friction. Okay, so that's how you reason out, what the force of static friction is going to be. All right, and once again, being a static friction problem, we have we have the values for all the components of the forces. Okay, so we've got like 60 here, 60 here, and then for this one, we've got all the perpendicular values and all the parallel values and so on. Okay, and so we're good to now calculate the coefficient of static friction. All right, so let me see if there's any questions in the chat. All right, still seeing just 2 people, so maybe I just have 2 people. Everyone else decided to take the rest of the day off. All right, so let's switch back to this, and I lost that, but that's okay. Fix it very quickly. Okay, and what's the formula? Well, this is the formula right here. The coefficient of static friction is just this. All right. And what's the static friction equal to? Well, we found that it was equal to 5 newtons. And what was the normal force equal to? If you look at the diagram, it was 112.6 newtons. And if you work that out, it turns out to be, I think, 0.04, oh, 12.6, 0.04444. Yeah, okay. And we'll just keep three significant figures. So there it is, okay? And so the coefficient of static friction has to be bigger than that value there. Again, it's an inequality, so it gives you a range. It doesn't give you an actual number, okay? Like if you were to experimentally measure it, maybe you would find that it's 1, maybe you find that it's 2 or whatever. All that you can say is that it's bigger than this number. It cannot be less than that number, okay? By the way, there's also this, I didn't mention it in the pre-recorded lecture, but it turns out that actually, no, it's not it's actually a strict inequality. It turns out that the coefficient of kinetic friction is less than, it's always less than the coefficient of static friction, okay? And that just turns out to be true experimentally, okay? And you'll actually do that in the, you're going to have a lab on friction, and you'll actually show that kinetic friction, you'll work out the kinetic friction and the static friction. You'll always find that the static friction is a bit higher. And the reason is that, you know, when two things are locked together, you know, it usually takes an extra big push to get them to break apart, but once they break apart, they start to slide, okay? And so that extra push, that's what makes the static friction bigger. So you know, in this case, we had the static friction of 0.44 like this, okay? And so whatever the kinetic friction is, it has to be less than that. The coefficient has to be less than that. And you know, in my problem originally, when I made the mistake, I had 0.25. And well, I mean, of course, 0.25 is not less than that. And so that's why it was wrong, and that's why I just changed it to 0.025, and then it works, okay? So I just mentioned that in passing because it's not that big a deal in the lecture to know that the coefficient of kinetic friction is less than static friction. But you know, you're going to show it in the lab, so we have it here, so I just thought I'd bring it up, okay? So there we go. There's part B, and let's turn our attention now to part A. Okay, so part A is the same, except that now you know the coefficient of kinetic friction, it's 0.025, okay, and we want to find the acceleration of the system. All right, so let's switch back to our whiteboard here, and the new diagram is going to look a lot like this, but you know, rather than try to erase stuff here, let me just start afresh, and we'll work it out, okay? And so we have this inclined plane like this, okay? We have the 13 kilogram over here, so that's my 13 over here. And here's my 6 kilogram dangling off the end, and there's the string that goes around like that, and here's my pulley. It looks a little bit bad, but you got the idea, okay? So this is the 6 kilogram here, okay? And there you go. There's your physical situation. Let's start doing the free body diagram. Let's start with the 6 kilogram. We know that gravity is going to be pulling it down with 60 newtons, like this. And we know there's a tension, like this, but we don't know how big the tension is. Okay? We don't know how big it is. Now, you might ask the question, is the tension going to be bigger than the 60, in which case this is being pulled up, or is the tension going to be less than the 60, in which case this is going to be pulled down, okay? And it makes a difference. So let's see if we can figure out what it's going to do, all right? So to do that, let's just switch back for a minute to our other diagram. This one right here, okay? The one we were just working on. All right, take a look at what direction the friction was in here. The friction, here I'll do it in yellow, I'll circle it in yellow. The friction was up, okay? So friction was up the inclined plane. And so if there were no friction, this thing would want to slide which way? It would want to slide down like this, okay? It'd want to slide down like that, all right? And so what we need or not what we need, but what we're going to get is if we have less than that 5 newtons, we're going to get this thing accelerating downhill like that, which means that this one is going to accelerate uphill like that. Okay, so let me say this again. I know this is the static friction problem, but if we had less than 5 newtons, okay, because the kinetic friction is going to be less than that. If we have less than 5 newtons, then the 13 kilogram is going to slide downhill, and the 6 kilogram is going to slide uphill like that. And what that means in terms of our situation now is that this is going to accelerate up like that, and we're going to have that Ft is going to be bigger than the 60 newtons. Okay, so we don't need that quite yet, but we will in a bit, and now you can see why Ft is going to be bigger than the 60 newtons. Once again, if there were no friction at all here, then this box would want to slide downhill like that. Okay, well, there's some friction, but not enough to stop it, so it's still going to be sliding downhill like that. Well, if this one's sliding downhill, then that one has to be pulled uphill. Okay, and so Ft is going to be bigger than the 60 newtons. All right, we'll use that fact later, but I thought I'd better mention it at this point because we're looking at those two forces. But other than that, you can't say how big Ft is. Okay, all you know is that it's bigger than the 60 newtons, but not how big it is. We're not in the static situation. Okay, once again, with the static situation, we had F net was 0, so that had to cancel that one. But here we don't. They don't because it's accelerating. Okay, so great. We're done with the 6 kilogram box. Let's take a look at the 13 kilogram box. We've got the two components of gravity. All right, and they're the same values as before because, I mean, nothing changed. Okay, it's still the same mass. And so this one turned out to be 112.6 newtons, and this one turned out to be 65 newtons, like that. Okay, so there you go. There's your force of gravity, and broken up into two components. Now there's the normal force, like this. All right, and that normal force is equal to 112.6 newtons, like that, because again, nothing changed from before. So like the normal force here has to balance against the perpendicular component of gravity, and there it is. Okay, now there's the tension up like that. Oh, that's terrible. Sorry, I'm not doing a very good job in my diagram, but not as good as the last one, but all right, there's the tension up. We don't know how big it is either. Okay, what we do know is that this tension here is the same as that tension there. The tension throughout the string is the same, but we don't know how big it is. Okay, and then there's a force of friction, and we know that that force of friction has to be uphill. Okay, and we'll call this FF, not FS for static, but just force of friction. Okay, and so there it is. And you say, well, do we have a value for the force of friction? And the answer is yes. I don't have enough room to calculate it here, but we can calculate it using this equation here. FF is equal to mu K times Fn. Okay. Now, for kinetic friction, you can use the mu K times Fn. For the static, you can't, because again, for the static, it's an inequality, and an inequality is not something, you don't solve for a value in an inequality, you solve for a range. But here, for an equality, you can solve for an actual value. All right, and so what are the numbers equal to? Well, what's this number equal to? It's 0.025, like that, multiplied by Fn, which was 112.6 newtons, and that's going to equal, let me get that answer, it's going to equal 2.815. So 2.815 newtons, like that. Okay, so I can't fit that in there, but that's what this is equal to right there. Okay, that's what it's equal to. All right, and so there we go. We've got all the forces identified except for tension, because we can't identify it yet. We can't give it a value yet. All right, but let's see what like what F net's going to be here. All right, so remember, F net is not equal to 0 in this situation. F net is equal to something, and the whole reason we did these free body diagrams so that we could get F net, all right? But, it's not, you don't have to add up all these forces here because two of them will actually cancel. That one will cancel that one, all right? And we do know that this is accelerating downhill like this. And so we know that the 65 is going to be bigger than these other two, okay? And so F net is going to be the 65 minus these two, okay? The 65 is winning, all right? So it's actually pulling the 13 kilogram box downhill, but it's being decreased by whatever FT is and minus also FF, okay? So it's going to be 65 minus the 2.815 here from the friction minus also the tension, and that'll be the net force on the 13 kilogram. For the 6 kilogram, this force here is going to be beating that one, okay? And so you're going to get that the net force is going to be FT minus 60. All right? So let me switch to the other whiteboard here like that. And you know what? I can very quickly cut and paste the answer so I don't waste your time with me typing a lot of stuff. There's this. And there is also this. All right. And let me make sure that I didn't lose. Okay, good. I didn't lose the screen. Okay, so basically this is just transcribed what I did on the other whiteboard. Okay, and so now we can say, okay, for the 13 kilogram box here, all right, I can say that F net is going to be what's winning? The 65 newtons downhill. That's winning. Okay, that's bigger than the force of friction uphill and also the tension uphill. Okay, so we don't know its value, but we do know that the tension is uphill. Okay, so that's how you determine the signs here. 65 is pulling it in the direction of the acceleration. The 2.815 friction is in the opposite direction of the acceleration, and so is FT. FT is also in the opposite direction. So for the forces that are in the opposite direction to the acceleration, it's negative, and the one in the direction is positive. Okay, so this actually simplifies to, and let me get the number from my other screen here. It simplifies to this. All right, did I lose the screen? I didn't. Good. Okay, and so like 65 minus the 0.2815, that's going to be 62.185 like that, minus FT, and there you go. There's F net. Now like students will usually get to this point and they'll go, well, I got all this, and then F net. And you go, well, why did you get F net? Don't lose sight of where we're heading. We're heading towards getting the acceleration, and so F net is related to the acceleration by Newton's second law. F net equals ma. Okay, now there's two m's, and so it's really, this one is m1. All right, like that. All right, you say, where did you get that? That's the second law, Newton's second law. All right, now what? Well, we've got this. There's your F net. So let me just show you. Okay, so for F net, I substituted in that expression there. I can't go any further. I don't have any numbers, so the best I can do is give F net as an expression, and then equals. So there's the equals. All right, and then M1 is 13, so that's 13, and then A, we don't know A. Okay, and there are two unknowns there. FT is unknown and A is unknown, and so we can't go any further. All right, great. What about this one? This is the M2. This is F net equals, and let me switch back to the diagram just one more time, so because you might have forgotten what it looks like. But see, the acceleration is up. So the force in the direction of the acceleration, that's the positive one, Ft here, and that 60 is negative, all right? So it's actually here going to be Ft is, F net is equal to Ft minus the 60, okay? So it goes like that. Now, we have Newton's second law here as well, but it's now M2 because we're talking about the 6 kilogram box. And you go ahead and you say, all right, well, what do I have for F net? I don't have a number, but I've got this expression, okay? And that's going to equal, and what am I going to put in for M2? 6, right? M2 is 6, oops. And A like that, And that's as far as we can go with those two. And so that's our equation number 2. Okay, so equation number 1 and equation number 2 are both, they're two equations in the same two unknowns, ft and a, and that means we can, solve them. We can solve them. You just isolate one value for one and plug it into the other. But for these problems, it's actually pretty nice because all you have to do is just add them. And so if you just take this side here and you add it to that, if you add the two left-hand sides and you set that equal to the sum of the two right-hand sides, you're going to get your answer. Okay, so that plus that is equal to 13 plus 6, which is 19. Okay, like that. All right, and you'll see that the FTs cancel out. All right, so then you'll get basically that 62.185 minus 60. So that's going to equal this, and that's going to equal 19a. And then finally, we're going to get that a is equal to, let me get that answer. A is going to equal a small number, but there it is. Okay, a is going to equal 0.115 meters per second squared. Okay, so it's going to be accelerating downhill with that speed. All right, and that's it for today.